Oh, hello everyone. Today I'm going to talk about our work in WCV, the ENCORE neural collapse perspective on out of distribution detection in deep neural networks. So this is basically part of my work as part of the Mental Laboratory, as part of my PhD program actually. So I will directly start with like defining the out of distribution data. So usually, what we do is that in training a neural network, we assume that our training data uh, comes from some specific input space, some specific distribution. So, like for example, like our input data, the let's call it X sub train, and we assume that it comes from some specific input space chi, and we assume that the corresponding labels they come from some specific specific label space y, and together the input and the labels they follow some specific distribution. Now, when we're actually training a neural network in a supervised way, for example, say we actually, even without a without even if we just assume it's not supervised training, when we're actually training a neural network, we usually make the assumption of closed world, where we assume that the data set that we're actually using, it comes it is the distribution it follows. It is the training distribution, and this is the same distribution that we're going to get after deploying the model. That is the test distribution. But in reality, when we are going to deploy a model, it's not going to be a closed world, but this is going to be an open world assumption where our test distribution is not actually going to be same as, possibly not going to be the same as the training distribution or in distribution. What it's possibly going to be is that it's going to be some like some samples, they're going to come follow the training distribution, which you call the in distribution or ID, and some of the samples not going to follow the training distribution, which you call which is they're going to follow some other distribution, any kind of distribution, which is going to be which is actually termed as the out of distribution or OOD distribution. So this is going to be we can like model it in literature. They actually usually model it as some mix the test distribution as a mixture of the ID distribution and the OOD distribution. And basically, so any data that follows that OOD distribution, or any data that does not follow the training distribution, we deem it as OOD. Now, so what do we actually want to do in OOD detection? So before saying that, actually, so basically we want to detect, but what do we actually want to detect? Like even in OOD, there are like we can actually further decompose that OOD distribution with a little I'm actually with a like in couple different types of OOD. The test distribution in that case becomes a mixture of ID distribution and another a type of OOD distribution we call the basically semantic shift distribution, or here I am just showing it as P sub novel. And there's another type of distribution that we call the covariate shift distribution, where I'm just showing it as P sub shift here. So what happens in a semantic shift distribution or novel category or novel category OOD? For a novel category for an OOD that is that is basically that comes from semantic shift. For that OOD, the semantic label that we can actually assign to that object or to that data is not even in our training label space. So essentially, there is a conceptual or semantic shift in the data itself. So our model did not, for example, it could be a completely new class. That's the easiest semantic shift actually. And the other kind of shift, that is covariate shift, we that actually for that kind of OOD data, the label space we still have um, the labels are still in our label space, but the conditional distribution of the input conditioned on the output label, that has changed. That is no longer the ID distribution we followed before, training data. So to be more exact, as I said, like for example, if our model has been trained on, say, to detect some animals, like for it could be, say, a dog, some cat, some bunny, or some other kind of animals, but it was not trained, let's say that it was not trained on birds, and we actually present it with birds. That means that, okay, we have introduced a semantic shift. In this case, actually, birds, they're like semantic OD data to our model. Whereas if it happens that we have for somehow our mod like the data that we had actually trained on, we are actually present if we actually present our model with severely corrupted versions of the same data, that means that we have actually created a covariate shifted OD data. So usually when we actually talk about when we actually talk about OD detection, what we mean is that we most of the time we actually mean the semantic shifted OOD data. We want to detect the semantic shifted OOD data. But apart from that, there is another there is another kind of evaluation practice in the literature also, that is called the full spectrum OOD detection, where they also consider the covariate shifted data as well. So in OOD detection, our goal, as I said, like, is essentially to design a score function which is going to with which we can actually separate the ID data from the OOD data. So the OOD data can come either from a semantic shift, or it can come from covariate shift. And the general formulation of the OOD score is such that the score is going to be higher for the ID data, and is going to be lower for the OOD data. So it can be otherwise, opposite as well, but that's that's basically the trend that we follow in the literature. So very briefly, actually, why do we actually need to detect this OD data as well, like anyway? So one very like this is going to, the detection of OOD is actually very important for us if we actually consider if we actually consider the safety critical applications specifically. It could be like autonomous driving, or it could be let's say surveillance, or it could be, say, application in medical domain. So what if our model actually detects some OOD data, something OOD as ID, it could, for example, in autonomous driving, detecting something OOD as something ID can detect can make our car steer that like in some unusual way, which can lead to some fatal incidents, or it could lead to some erosion of trust in our system, if our system starts detecting, let's say in this case, basically a deer as some pedestrian or motorcycle. So this not like fatal incidents. These are obviously bad, but the erosion of trust in the system, that is in a way, even if it's not fatal, even if it's not fatal, it is really bad for a system from at least commercial perspective. So what we need to do is that we need to make our model understand what it does not know actually. So not just being uncertain, but exactly making our model understand exactly what it does not know, what it had not seen in the training data. So in this work, we explicitly do this task in a post-hoc manner. What we want to do is that we assume that we are not going to, however way the model was trained, we don't know. Whatever training algorithm the trainer used, we don't know the training algorithm, but we do assume access to uh, either all or at least part of the training data. And using the training data, we use the training data only to get some heuristics from the model. That's it. And basically, why is this post-hoc OD detection challenging actually? Why couldn't we use just the let's say the model itself already gives us the confidence matrix as output, like the softmax probability. So why can we not just use that? Like, for example, like if let's consider the case of surveillance drone, what has been seen is that this is actually a bit of iteration, or like in training phase, let's say that we are training it on cars and trucks and stuff. That's going to be our in distribution classes. But in deployment phase, it could be it could like how even if it says tanks or military vehicles or some other sort of different kind of vehicles, it is still vehicles, but it's still going to be OOD for in our case. But what happens is that it has been shown by Niggin et al. And like our neural networks, it's not just the OOD data. Even if you we just present it with very noisy data, just pure noise, that's it. But which doesn't make sense to our as humans. Even that is going that can elicit like very high softness probability from our model. So our models are, well, it is already established that it's overconfident, but and this overconfidence usually not you maybe not always, but most of the time this gets carried over to the OD data as well. So the confidence of the model, it does not really it is not a really good measure to understand what is ID and what is OD. So what do we do in this case? Like some of the post-hoc approaches, that is some of the post-hoc approaches that are actually like very that some of the post-hoc approaches that are being used in current literature. We can actually the most important post-hoc approaches are basically the most performing good performing post-hoc approaches. We can the first of them we can the first type of them would be the ones the post-hoc approaches that use the output logics. So the maximum softness probability was the very first that is the one that started all this post OT detection and misclassification detection, to be honest. And then later on in 2020 came the energy-based out of distribution detection, and in 2023 we had the paper Gen. It pushed the boundary of what we can do with just logics. So they define these core functions based entirely of the output logics of probability. So they do not use any kind of information from the feature space or from the input space or any auxiliary models or anything. So these properties, they actually make them very efficient, and also they do not these methods, they essentially they don't actually access the training data as well. So that's another plus point for them. But the problem is that maximum softness probability and energy, they fail in many cases, not just the covariant shift and semantic shift, but Gen specifically, it does very as compared to the maximum softness probability or energy, the Gen, it does much better in on the benchmark, but still in many for the covariant shifted OD, it still does lags behind a good deal. So now, the second kind of approaches that are one of the most prominent in the OD literature now, there's the distance-based approaches, where these are mainly based in work in the feature space, like the Mahalanobis distance-based approach, or relative Mahalanobis distance-based approach, or KNN distance-based approach. These things, as I said, they work entirely in the feature space, and the core idea is that their core idea is that the OOD data in feature space, they should be separable from ID data based on the distance itself. Like the ID data, they should cluster together, and the OOD data should be further from the ID clusters. So they do not use any information from the output logics. But, and as I said, they core idea they utilize is that the ID data they should be closer together, and the OD should be far from the ID data in the feature space. And for example, the k-nearest neighbor distance show that, okay, there can be if someone actually uses a contrastive learning method, the specific kinds of training methods, they are help specific distance-based training, distance-based approaches like KNN actually showed that, okay, contrastive learning improves their performance by a great deal actually. So now there are other two kinds of post-hoc approaches. There's subspace-based approach, for example, the Vim, the NACO, and the like Corp, which is actually kernel-based method. So they're based on the idea that the OD data should have large component in the null space as compared to the like principal space. So this is a heuristic that has been used for a while now, and based on just the null space energy and using that null space energy using some transformation on the null space energy, or basically like coupling it with the output logics. They have come up with like different approaches. Like the Vim itself, it actually couples the null space energy with the output logics. The NACO, this actually doesn't couple it directly, but this just couples the null space energy with the maximum logic only. And basically the corp, this does not directly say that it uses null space energy, but it says uses a reconstruction error, which is essentially the gives us the null space energy anyway. But the reconstruction, instead of just using the principal component analysis like NACO and Vim, they used like random Fourier features to estimate uh, to introduce nonlinearity in the estimation process, and use a kernel function to introduce the nonlinearity in the subspace estimation, and which kind of gives them a much better performance. And finally, the activation shaping based approach, which basically, like for example, the React was one of the like most earliest approaches in this category, and then there was Ash and there was Scale later on. So their main idea is that if we actually shape the penultimate features, we appropriately we can separate the ID and OD data sufficiently. They use all these approaches. They actually use the energy based score after like clipping or selectively scaling the penultimate features. So the problem with the current literature is that like there are mostly heuristic based actually, and as compared to them, what we do in our work is that we ground our approach on the theory of neural collapse. So as well, while the existing methods they don't really have a clear failure point, and like we connected to the DNN property, our approach to the DNN properties. So we have a specific failure point, like when if a model is not sufficiently close to the theory of like sufficiently agree with the theory of neural collapse, it has not been trained up to say the terminal phase of training, or close to the terminal phase of training. Then the farther away from the terminal phase of training it is, worse our performance is on for OD detection on that. So while the existing approaches, they show a large variation across benchmarks by like the same method. We can actually we see that the same method it can do better good on ImageNet. It doesn't do as well on the anti say Cipher or ImageNet 200. So basically, even on the ImageNet dataset, it can be that okay, we have like different OD data sets for benchmarking, but some it does good on some, but does bad in more in other in some for some OD datasets an approach can work, but for some other OD datasets it may not work. But ours is more stable across the benchmarks. So to summarize, actually, the prior work, while the prior works, they asked like what a score works. We actually try to ask the question like how do we use the DNN properties to control the score itself. So actually, we don't really try to introduce a new score altogether, but rather we try to modify the existing score to introduce based on the theoretical properties that we find from the theoretical properties of DNN to have from the neural collapse. So just a little bit of background on the energy-based score, because the two of the major components of our baselines, foundations of our work is like the energy-based score and the neural collapse. The energy-based score, this essentially, like I'm taking this one from the original paper actually. So what it does, the energy-based score, what it does is that it takes the output logics of a neural network and takes its log sum exp of the temperature scaled logics. So sorry. So What they show actually is that this is the energy-based score. It is actually affinely connected to the logarithm of the probability of the input. So they reason that, okay, if this is the case, then we can and basically and for any OOD data, the probability of the input and the P of X should be very probability density should be really low, and and for ID data, this probability should be really should be high. So we can use this energy based score to separate the ID and the OOD. So the problem is that they actually derive this score by connecting the softmax distribution with the Gibbs distribution and or in energy-based modeling. But the problem is that this is done based on just structural similarity, and this and there was no empirical evidence for it either, actually. So what we see in practice is that this may not always similarity may not always hold, but it give hold like completely, and lodges sometimes they can become like spuriously large as a result. Even for the OOD, as a result, the ID and OOD are like they overlap a good deal, leading to our overconfident OOD samples, even with energy score. So it works theoretically, but the problem is that it lacks in performance, and it basically doesn't establish itself with any like connect itself with any like known proven theoretical properties. Now, the other foundation for our work, that is the neural collapse. The key properties of neural collapse, the key things that it says us is that the first one is the variability collapse, where we they say the property of the neural collapse. What the actual paper actually tells us is that the phenomenon of neural collapse is when if we keep training our neural network, and if we actually achieve almost a zero error on the training data, essentially zero error on the training data, they term it as the terminal phase of training. And at the terminal phase of training, they show that, okay, the paper for the prevalence of neural collapse during the terminal phase of deep learning training, it shows that we have like four properties at that phase. The first one they say is that the variability collapse. It essentially tells us that the of all the features of a specific class, they collapse to the class mean. So their variability tends to zero. The second one they say is that the convergence to simplex ETF or equiangular tight frame. Essentially, at that point, at the terminal phase of training, the class means they form a simplex equiangular tight frame. So essentially, all the class centers they are like from the global mean, all the class centers at equidistance, and they are equiangular from each other, which actually gives us like two relations the distance of the class mean from the global mean. This is same R for everyone, and the angle between two different class means, or in this case actually if you take the normalized class means and take the cosine similarity, it's going to be take any two classes and get their cosine similarity between their like class prototypes. It's going to be the same, -1 over c minus 1. So then the convergence to self-duality, which essentially tells us that the classifier weights themselves, they align with the class means up to some scaling constant, obviously. And then we have the simplification to nearest class center, which essentially tells us that now the classifier, which actually comes like can be derived from the previous three like properties, which essentially tells us that the classifier, it essentially reduces to nearest class center classifier. That means that if we are given a specific test sample, we can just tell which class it is based on its distance from the like which class it's the nearest to. Then later on, another property was later added to this by this paper. Nego actually adds this one, that is the ID-OD orthogonality. They say that if we keep training at the terminal phase of training, the OD data, the class prototypes of the from our like the OD features, they are actually all like orthogonal to the classmates. Take any class and its class prototype. It's the OD feature. It is going to be close to orthogonal to that classmate. So essentially, the OD data is orthogonal to our feature subspace in like or orthogonal to our equiangular tight frame itself. So this is like a visual from the paper itself. Like the green spheres, they are essentially our final classmates, and the red ones, they are actually our the classifier weight for different classes, and the purple and the blue ones, they are actually our current feature, trained features. As time progresses, training progresses, these, as we can see, is that what it shows is that the trained features, they're going towards our class means, and also the weight vectors themselves, they're aligning themselves, the classifier weight vectors themselves are aligning themselves with our final equiangular tight frame, and the final result would be something like this actually. So now this is something that we use like based on which we actually derive our insight. So what we do is that we take the properties of the neural collapse, and now we apply it to our energy score. So what do we find actually? So now if we take as represent the Z as our logits, W as our classifier weights, H as our feature penultimate layer feature vectors, and B is basically our classifier bias. We first thing that we can write is that at the terminal phase of training, we are going to have the class feature vectors H almost equal to we're going to all of them are going to be basically similar, of same length. So we're going to represent that as mu sub c. And what we observe is that as the classifier from neural collapse, the classifier weights vectors themselves, they're going to, after some scaling constant, they're going to be equal to the classifier like our class mean prototypes, and that we are representing that with alpha here. And actually, how we actually get to this equation, WC equals to alpha times mu c tilde, you can actually find the detailed derivations. I'm skipping the detailed derivation for the sake of the basic, the core insight. So based on this equation, WC, or like based now, based on the basically the second property of the neural collapse, we can say that take any two the class prototypes from any two, mu I and mu j. What we're going to actually find is that for the same class, when I equals to j, and their inner product is going to be equals to r squared, as we assume that the centered class means their length of the centered class means are actually r, and if not, they're not the same class, then it's going to be negative r squared over c minus 1. So now from this, what we actually find is that, like, if we apply this to our first equation, w times h plus b, what we'll find that for the same class, like for ID data actually, for the like ground truth class or the predicted class, essentially, we're going to have z sub c prime, which is always going to be our predicted class or ground like max or the ground truth class. It is going to be equals to alpha times r squared plus k, where k is essentially again a model specific constant, and for when c prime equals to c, and if c prime is not going to be is not our ground truth or the predicted class, then it's going to be negative alpha r squared over c minus 1 plus k. And for any OOD data, this is ideally this is going to be equals to just k, because the OOD data are supposed to be orthogonal to the any existing class. So in that case, mu I transpose times mu j, it would give us 0. So based on this, what if we compute the energy score, we get this equation here. And if we simplify this, assuming like r is much great, or like if we increase r, keep increasing r, then we can simplify this to this equation, which tells us that the difference between the ID and the OD energy is going to be almost equals to alpha times r squared minus log c. So this means that scaling up the features, they provide us better separation between the ID and the OOD. So based on this insight, I'll just quickly go over the methodology, and that is basically what we do. We have in our ENCORE like two phases. In the setup phase, we take the ID data and we pass it through our pre-trained backbone network and get the penultimate features. We compute the PCA on those features, and basically store the principal create this principal subspace for that. So we just keep the top k basically top k dimensions from that. Now we we store that subspace basis for a use in our inference phase. During inference, what we do is that we again take a test input, pass it through the backbone network, get the penultimate layer features, and we project those features onto the ID subspace. Then we compute an alignment ratio. That's how much does the feature actually aligns with the principal subspace. And based on that, we use that alignment ratio to compute a scaling factor, that is exponential of lambda times rho. And then what we do is that we use that to scale our cosine logits. Now, by cosine logits, what we mean is that we just dump the like bias value, and we just take the classifier weights themselves, and we just take the test feature and just compute the cosine similarity between the two. Instead of computing w times h, we're essentially computing w times times h over norm of w times norm of h. Then we use this cosine logits to compute our final energy score. Now, and then the energy score, as usual, is used for the detection of the OD. So now there are a couple of things here, like why we use the cosine similarity, because and we essentially to remove the norm bias, because if our models, they usually do not get to the terminal phase of training, and as a result, there is still a little bit of bias in the classifier, but that should not neural collapse assumes that there are like at the terminal phase of training there is going to be no bias. Actually doesn't assume, it says that at the terminal phase of training there is going to be no bias. So we try to align, do it partially to align with the third property of the neural collapse. And also the reason for adaptive scaling, the reason we use a scale factor, first of all, it is giving us, we have already seen that scaling up the features themselves, it's supposed to give us like better separation between the ID and OOD. So another reason is that the reason we use adaptive scaling is that because to align ourselves more with basically the fifth property of the neural collapse, which says that strong features alignment should be between for the ID subspace, and for OD data should have should not have a strong feature alignment with our principal subspace. So as I said, like we do it partially to align ourselves more with the OD like fifth property of the neural collapse. And some of the key results that we observe from in our work is that our work, this is for the Cypher 10, and we first of all we use the OpenOD benchmark itself, and this is key result, the result for the Cypher 10 benchmark with ResNet 80 that comes with the OpenOD benchmark. And at our approach, it provides like 6% relative improvement compared to the closest baseline in far OOD, and as similarly for the near OOD as well. And for with our method, if we when we compare it for like scale it up for the image into scale benchmarks, our approach ENCORE, it gives like again, it gives like more than actually 6% relative improvement for close to like it gives less improvement for like ImageNet benchmark, but still it when we actually take a look at the like OOD data set, it is still consistently beats the other approaches like across the OOD data sets, but while the other approaches, as I said, like they are good for some of the OOD data sets, but for some they're not that good. So another thing is that we do when we're actually evaluating for our approach for the full spectrum OD detection, our approach does as compared to the rest of the approaches, it beats the rest of the approaches. Like in this case, we have like 5 data sets in total, and it does best in terms of FPR. Like in 4 out of 5 data sets, and in terms of AUROC, it is the best in still best beats the rest of the approaches in 3 out of 5 data sets. And now So when we actually compare ourselves with the two closest approaches like the scale and NACO, we see that we still have like 10-point improvement, at least 10-point improvements from each of them. Well, NACO also takes an approach, neural columns-based approach, but they don't modify. They try to propose a new score, but which will still beat by at least 10 points for in both narrow OD and far OD. And when we compare ourselves with some of the sort of approaches like the virtual logic matching and the KNN, our performance in terms of latency is we're much faster than those two. Like then this is like the partial comparative result for the imaging with context. You can actually get the detailed result in the paper. And so just part of the ablation study that I'm showing here, like if we vary the scaling constant, this is basically one of the hyperparameters in our approach. But what we actually observe is that we actually set it in our experiments to 3, and actually what we observe is that across both cipher and like imaging benchmarks, setting it to anything above 2 does not vary the performance of our approach much. So the key takeaways from this from our work is that neural columns gives us a theoretical basis for improvement of OD detection, and uniformly scaling the features, it improves our ID-OD separation, and adaptive scaling provides us the further gaining performance. So essentially, we're like tying up like two things, like the core ideas, two core ideas from the neural columns, like taking the uniform scaling, and also the old like fifth property of neural columns, that is that actually inspires us to do the adaptive scaling. But on the drawback is that our result is contingent upon the agreement with the neural columns theory. But what you observe is that as the further we go away from the neural columns theory, our result, our performance degrades, but so does the performance of the other approaches as well. So thank you, everyone.